So what we are going to discuss in today's lecture is an extension of what we've discussed in the uh, last lecture. So here today we're going to discuss about something which is known as Bayesian or Bayes classifier. Right. So remember the setting which we have developed in the previous uh, previous class. So what was the setting actually? We have a machine learning problem. We have a set of data, and we know some samples of the data, um, and for them we have the corresponding labels. But for the entire set of data, we don't know what the corresponding data labels are. So we need to have a hypothesis function which is h, which maps data points to its corresponding labels, right? And how do we find this hypothesis function which does this mapping? Uh, because both these sets are having infinite cardinalities, and there can be infinite number of functions which can learn between these two sets. So how do we find this, the hypothesis which is best suitable, right? So we have to classify whenever there is a question of which is the best, then this can be cast as an optimization problem, right? And then what is the optimization function or the objective function which the constraint function? The constraint function turns out to be which is known as risk, r of h, which is the expectation or the distribution pxy of the loss between h of x and y. So we want a function, so we want a hypothesis which minimizes this function, this objective function, right? Yeah. So how do we find it? That's what we are going to discuss in today's class. Fine. Yeah. And so to find this, let's do one thing. Let's define a particular, the simplest possible loss function. The simplest loss function. You have to be grammatically correct. Loss function. It's something which is known as a 0-1 loss function. So what a 0-1 loss function does is L01 function can be defined as here actually we have we're trying to map h of x with y, right? So whenever h of x is not equal to y, this is so remember, this is a loss function. We have to give a cost when it is not matching, and it's 0 otherwise. So whenever the predicted label or the hypothesis, the function, the label predicted by the function for a particular data x, it's matching with y, we don't have an issue. If it's not matching with y, then we are going to penalize it. This is the simplest possible loss function we can think of, right? Yeah. Now we want to find a function, right? A hypothesis h which minimizes the risk. The risk, we've already seen what the risk is, right? So let's assume there exists some kind of a function, right? Such that r of h, let's call that as h1 for the time being, of a data point, for any data point to be precise, is always less than or equal to r of h of x for all h for all pxy. Understand the setting very well, because here we're trying to minimize this over a set of functions. It's similar to what we have subjects like variational analysis and all this stuff. It's not like we are trying to minimize it over a range of variables. The setting is different. Okay, we are trying to minimize it over a range of functions, right? It's just like we have a data point, for example. We have 1 as a data point, and we have e raised to exponential e raised to x. Let's say x is equal to 1 in e raised to x cos x, then sin x. These are like the sinusoidal family of functions. We can have polynomials like x squared plus x plus 1. We can have logarithmic functions. Which, among these functions, which is the minimum value? This is this kind of setting. Okay? Hope that is clear from this. Okay. Now we have to find out an optimizer like this, right? Okay, so for this, let's get into this. Let's expand this R of h a bit, along with this corresponding loss function which we have, right? We have R of h is the expectation of over the distribution pxy for the loss function h of x comma y. I hope this is very clear. There's no doubt about it. See, if you see here, the way we have defined this loss function, this can be replaced by an indicator random variable. Why? What is an indicator random variable? Basically, it's a Bernoulli random variable. It's a special case of a Bernoulli random variable. Why can we model this with a Bernoulli random variable? Because it's taking only 2 values, right? And whenever h of x is equal to 1, not equal to y, whenever that even happens, its value is a 1. So this can be written as whatever loss function we have as the expectation of a Bernoulli random variable h of x not equal to y. Or the indicator random variable, to be precise, right? Now we can use the base rule. This P of this particular probability Pxy can be again split up as Px into expectation of P of y given x, indicator h of x not equal to y. I hope this is clear. This is again what we call as the properties of expectations. Okay, we can split up this like this. Now, what is this expectation? Whatever we have in bracket. What is this? You can again simplify. This is just algebra. This can be written as since this is the probability of y equal to 1 given x, since it take only 2 possibilities, and h of x equal to 0 plus p of y equal to 0 given x, indicator of h of x equal to 1. I hope this is clear, right? See, this is right now. This is how this setting of risk function looks right now. Now we have to choose a h such that it always chooses the minimum. So one thing we have to understand is the hypothesis can only choose a label 0 or a label 1. I hope that is very, very obvious from this. Okay, the hypothesis, whenever we are given a data point x, the hypothesis chooses uh, either this one, h of x is equal to 0, or h of x is equal to 1. So basically, since it's an indicator variable, it can take a value 0 and 1, right? So basically, it's like a term. Suppose these are two terms, term A and term B. Basically, it just chooses term A or term B, right? If h of x is giving a value 0, then it chooses term A, and if h of x is giving a value 1, it chooses term B, right? Now, what we have to do is we have to define a hypothesis so that when h of x is equal to 0, this value is minimum and this value is maximum. So naturally, when h of x is equal to 0, this term will be selected and the maximum term will be obviously neglected. Similarly, when h of x is equal to 1, we have to select this term along with h of x, this term along with h of x, that is p of y equal to 0 given x, needs to be minimum, and this term has to be the other term along with h of x equal to 0, indicator variable h of x is equal to 0, that has to be maximum. So by construction, we have to find the h of x which actually selects the term which is actually a minimum, right? So how do we construct it? So for that, we'll construct something known as a Bayesian classifier. So Bayesian classifier, what it does is, it is having a value 1 only if p of y is equal to 1 given x is greater than equal to p of y equal to 0 given x. And it is having a value 0 if p of y equal to 1 given x is less than So let's understand this again. See, h of v can take only values 0 and 1, right? Suppose it is taking a value 0. So what will happen when it's taking a value 0? Only the term, term A will be selected, right? There's no doubt about it. Term A is getting selected. P of y given x is actually, y equal to 1 given x is actually less than p of y equal to 0 given x. That's how you constructed this. And let's say it is taking a value 1. And when it's taking a value 1 here, term B will be selected, right? Since it's an indicator and a variable, this term will be selected. The other term will be obviously 0. And what is along with it? P of y equal to 0 given x. But in this case, this is obviously less than the other term. So by construction, always the minimum between these two terms, between these two conditional probabilities, are selected. So by construction, it turns out Bayesian classifier minimizes RFH, or we can say R of hp of x is always less than or equal to r of any possible hypothesis. Hope this is clear. Right? Okay, so now, so let's summarize a bit what we have seen. Let's go through this. What was the key idea? This is important. This is very, very important concept. We have the hypothesis. We have a function known as the risk function, which we need to optimize. And we have taken an L01 loss. From the L01 loss, we have actually using algebra and Bayes rule and all the stuff. Yeah, first thing we have to notice here is that the L01 loss can be represented as an indicated random variable when h of x is not equal to 1. Right? And we have used Bayesian law to express this probability as the product of a prior and a conditional. Right? Now we have splitted the terms using the two values which h of x can take. This is till this actually it's valid for any kind of hypothesis, but we are choosing a hypothesis by construction. We're designing a hypothesis such that this always chooses the minimum between these two terms. Right? Yeah. Now there are a few more things which we need to take care. How do we estimate p of y equal to 1 given x? Right? What does that mean? We are given data, and what is the conditional probability that p of y is taking a particular label value? Right? How do we find this? Okay, for this, let's look it into a bit more detail. So what we need to find is p of y equal to 1 given x. So by a Bayes rule, we can write it as p of x given y into p of y divided by p of x. Right? We want to find how the Bayes classifier is defined. We need to evaluate these classifiers, and whenever this value is greater, we have to assign that to a 1. Otherwise, we have to assign it to a 0. That's how we have to do this. But for finding p of y equal to 1 given x, we have to evaluate all these properties. In fact, this marginal need not be evaluated because you are just finding the ratio. This can be also, if you go here, this can be also expressed as a ratio, right? P of y given y equal to 1 given x divided by p of y equal to 0 given x greater than equal to 1. We can express it in that form also. So this marginal part, the denominator part is not important. Need not be evaluated. Yeah. By the way, it should not be equal to 0. I mean, that doesn't make any sense, right? Probability of a data being there, data point being there, that doesn't unless a data can never happen. Yeah, we can think about that as well. So we have to estimate these probabilities. So we have some specific terms for this. So we call this p of x given y equal to 1, or x given y as something known as the class conditional probability. So how do you remember which is coming at the denominator, which is coming as the condition? You can use this. It's a class conditional probability. So the class is the condition. That's one way of remembering this. And p of y is known as the class prior. P of y is known as a class prior. And the left part of this is actually posterior, right? This is known as a label or class posterior. Label or class posterior. So we have to evaluate this, but in order to evaluate this, we have to know this class conditional probability. In fact, it's class conditional density. Sorry, it's not probability. It's class conditional density. Because we have to be precise. We have to evaluate this class conditional density, and we have to also evaluate the class prior. Only if we know these values, then we'll be able to evaluate this. So basically, remember the earlier setting um, which we discussed while we were considering the probabilistic viewpoint of the machine learning problem. So there we said we have to we have to estimate the distribution function p of x, p of xy, right? That is the only thing we have to do to completely learn the machine learning problem. Here, we are just breaking it down further and saying to find the best classifier in a 0-1 loss function setting, right? We have to estimate the label or class posterior. But in order to find the label or class posterior, we have to find the class conditional density and the class prior. So how do we estimate this class conditional densities and class priors and all these things actually provides fuels the further lectures of this course. So we'll look at the estimation part and all this later. That's what we will discuss. Okay. So this is for this lecture for the time being.